Now, in the previous session, we saw the Taylor series for e to the power of x. Now, let's look at it for natural log of x. Now, here we will look at it about a is equal to 1. E to the power of x, we saw it for about a is equal to 0. Now, why are we changing that? That's primarily because at a equal to 0, that is natural log of 0 is undefined. So, that is why we are taking a equal to 1. So, we have f of x equal to natural log of x. Now, what is the first thing that we have to do? We have to figure out the successive derivatives of f of x. So, the first derivative of f of x is 1 by x. Second derivative is minus 1 by x square. How did we get this? This is a prerequisite for us to do Taylor series. But very briefly, we can take it up as x to the power of minus 1. And we saw that to find the derivative, we take the exponent down. So the minus 1 comes down. So minus we have. And we subtract 1 from it. So minus 1 becomes minus 2. And when we bring it down again, it becomes x squared. The third derivative of natural log of x is 2x cubed. So x to the power of minus 2 comes down. So we have minus 2, which becomes 2, times x to the power of minus 2 minus 1. So that is minus 3. So we take it down, it becomes x cubed. Similarly, fourth derivative is minus 6 by x4. Since we are interested in a equal to 1, what is the 0th derivative of f at 1? It is, see, 0th derivative means the function itself. So f of 1 is natural log of 1, which is equal to 0. Now, first derivative at 1 is equal to 1 by 1, which is equal to 1. Second derivative at 1 is minus 1 by 1 square, which is minus 1. Similarly, third derivative at 1 is 2. Fourth derivative at 1 is minus 6. So, which means the general nth derivative is fn of 1 is equal to, now by looking at this pattern, we arrive at this minus 1 to the power of n plus 1 times n minus 1 factorial. And we know the Taylor series formula. F of x is equal to sum from n equal to 0 to infinity of fna by n factorial times x minus a to the power of n. So let's apply it to this case. So f of x is natural log of x is equal to summation as n goes from 0 to infinity of minus 1 to the power of n plus 1 times n minus 1 factorial by n factorial times x minus 1 to the power of n. Here in the summation notation, we have n equal to 0 to infinity. We change n equal to 0 to n equal to 1, since natural log of 0 is undefined. So the statement becomes natural log of x is equal to summation from n equal to 1 to infinity of minus 1 to the power of n plus 1 times n minus 1 factorial by n factorial times x minus 1 to the power of n. Now here what happens? This n factorial can be written as n times n minus 1 factorial. So n minus 1 factorial gets cancelled out and we are left with n times x minus 1 to the power of n. So natural log of x is equal to summation from 1 to infinity of minus 1 to the power of n plus 1 by n times x minus 1 to the power of n. Now we expand this. We get natural log of x is equal to 1 plus 1 is 2. So minus 1 square becomes plus 1. So we don't have to write it. So we end up with x minus 1 to the power of 1. That is x minus 1 divided by 1. So we have x minus 1. Then we take the second term. When n equal to 2, we say minus 1 to the power of 2 plus 1 by 2 times x minus 1 to the power of 2. So here minus 1 is to the power of 3. So that means it will be minus x minus 1 square by 2 and so on. So this is for natural log of x. We have arrived at this Taylor series. Now for f of x equal to natural log of 1 plus x, if we add 1 to x, we end up with natural log of 1 plus x is equal to 1 plus x minus 1. So 1 will disappear. We are left with x. Similarly, in every place we will make sure that the minus 1 gets cancelled out. So we'll end up with x minus x square by 2 plus x cube by 3 minus x 4 by 4 and so on. So this is the Taylor series for natural log of x. This is for natural log of 1 plus x. Now what about, so radius of convergence will be what? Natural log of x is equal to this expression. We ignore the x term, x minus 1 to the power of n, because remember x is, we are fixing it to a particular point at x equal to 1. So the convergence will depend on the rest of the expression. So we take an is equal to minus 1 to the power of n plus 1 by n. And we take the next term, an plus 1. So an plus 1 is equal to minus 1 to the power of n plus 1 times 1 by n plus 1, which is equal to minus 1 to the power of n plus 2 times 1 by n plus 2. And we divide an plus 1 by an, which is equal to minus 1 to the power of n plus 2 times 1 by n plus 2 divided by minus 1 to the power of n plus 1 times 1 by n. We convert it into multiplication by taking the reciprocal. What we end up with is an plus 1 by an is equal to minus 1 to the power of n plus 2 minus n minus 1 times n by n plus 2, which is equal to, here n minus n goes off, 2 minus 1 is 1, so we are left with minus 1 times n by n plus 2. This we simplify it a little bit further. We say an plus 1 by an is equal to minus n by n plus 2, which is equal to minus n by, now from these two, we take out n common. So n times 1 plus 2 by n. So that n and n gets cancelled and we are left with minus 1 by 1 plus 2 by n. And now we take the limit as n goes to infinity of the absolute value of this an plus 1 by an. So as n goes to infinity, what happens? 2 by n becomes 0. So we are left with minus 1 by 1. The absolute value of that is 1. So which means that the radius of convergence r is equal to 1. Interval of convergence will be, since the expansion is centered at x equal to 1 and r is equal to 1, the interval is between 1 minus 1 and 1 plus 1, which is 0 to 2. Now, natural log of 0 is undefined. So x equal to 0 is not included. Natural log of 2 is defined and converges to it, so included. So the interval of convergence is 0, 2, where here it is open and here it is closed. Another way of looking at radius of convergence is to see the distance from the nearest singularity or discontinuity. So as we have seen, as we get closer and closer to 0, the natural log of x goes to minus infinity, which is what singularity means. So the distance is the radius of convergence. Now let's go back to our graph. So as part of the first introductory session on Taylor series, we saw this graph. Yes. we saw that the radius of convergence, we can form a circle, and the graph within that is a place where convergence actually happens. And we had also seen that as I start from the first term, after the seventh term, it starts diverging, and the behavior doesn't change, it keeps diverging. So it doesn't matter how many terms I take, it will converge only in this radius of convergence. Now, what about if I, say that not at about 1, but say about 2? So my radius of convergence also increases. So as I mentioned previously, that one way of looking at radius of convergence is the distance to the nearest singularity or discontinuity. So here, if I start increasing the number of terms, see, accordingly, this circle also increases as I keep changing the position of the centering of the Taylor series. Okay, as I change A, here it is not changing. It remains as 1 because it is static, but the graph keeps getting updated. Okay, so here it is actually A is equal to 1 is this graph. So that was the Taylor series for natural log of x about A is equal to 1. That's it for now.